Okay, so today we are going to begin Chapter 8. Chapter 8 is on hypothesis tests. And here we're still doing statistical inference, and the idea here is, we want to make a conclusion about the population just based on a sample of data, all right? And so that's the big picture idea. In pretty much all of statistics, we want to make a conclusion about the population based on a sample of data. So without having to observe the entire population, can we make a conclusion? And what we do with a hypothesis test is we start off with a pair of hypotheses, okay? And this is why it's called hypothesis tests. We begin with a pair of hypotheses, and these hypotheses are called the null hypothesis which we abbreviate H0, and the other is called the alternative hypothesis. Oh, there's one more thing I wanted to say about the tests. Some of you guys have sent me emails over the weekend, and I just, I got so many emails over the weekend. So I apologize. I haven't gotten around to responding to all of those emails. I will get to it. It'll just take me a couple days to respond. My inbox is bursting at the seams right now. So okay, let's see. So we begin with a pair of hypotheses, the null hypothesis and the alternative hypothesis. Now, the null hypothesis is kind of like a claim. Is a claim that, or a statement about the population, and that is the statement that we are going to test. The null hypothesis is like a claim or statement about the population. I guess I don't need to put claim in quotes. It's like a claim or a statement about the population. Okay, so for example, we could have, a bucket of candy again, full of M&Ms, and someone can come along and say, the claim in this case would be, the proportion of red candies or red pieces in the bucket is 19%, okay, proportion or percentage. So they're just saying in the population, this is the percentage or proportion that exists, okay? Now I keep using this candy example, but it could be generalized to anything, right? The proportion of people who like this or feel this way or have this opinion is some percentage or some proportion. We make some kind of claim. And symbolically, we would write this as the null hypothesis states that P is equal to 19%. So we would write this. The alternative hypothesis will be something that counters the claim. So for example, if the null hypothesis states that the proportion of red pieces in the bucket is 19%, the alternative would be the proportion is not 19%, or the proportion is more than 19%. It's something other than 19%. The proportion that's red is not 19%, or something like that. And if we were to write with symbols, we would write the alternative is that P does not equal 19%. Or, later on we can try, P is greater than 19% or P is less than 19%. Something where we are not agreeing with the null hypothesis. This is what we set up here. And what we want to do is someone says, okay, in the bucket we haven't counted up the population. We don't know exactly what's in the population. I'm saying the proportion is 19%, and we want to test that claim. We want to test the null hypothesis. Okay. And the way we're going to test the null hypothesis is we're going to make a critical assumption. We're going to say, let's assume that the null hypothesis is true. If we assume that the null hypothesis is true, what do we expect to see? Okay, and in essence, we create an idea of our expectations. Okay, we have an idea of what to expect. We have some expectation, and then so we have expectation, and then we compare it to reality. Okay, and if the reality aligns with our expectations, then we say, okay, I have no reason to doubt that my assumptions were wrong. Okay, it doesn't prove that my assumptions or the ideas that I had were true, but it just says, I have no reason to doubt that my assumptions are wrong. Okay, and on the other hand, if we have this idea for the expectation and we look at the reality and they are completely different, the reality of the situation is very different from what we expected to see, then we have to side with reality, and we say, okay, the fact that my expectations were so far off gives me reason to believe that the assumptions that were made to come up with this picture of the expectation, those assumptions were wrong. Okay, and it was my wrong assumptions that led me to a different expectation than what really happened. And that's how we're going to test our null hypothesis. Okay, so we're going to say, so we will assume that the null hypothesis is true. Okay, and so if the null hypothesis were true, so I'm going to just write H0 for null hypothesis is true. What do we expect to see? Okay, and what we will do is we then compare. So this sets up our expectation. We then compare our expectation to reality. Right. And so, the reality will be based on our data. If the expectation and reality align, that's a good thing, right? Or, it's not necessarily good or bad, but if the expectation and reality align, we have no reason to doubt the null hypothesis. Okay, because the null hypothesis, which was used to create our expectation. And on the other hand, if the expectation and reality are very different, okay, then this indicates that the assumptions that were made for the expectation to create the expectation, that is that the null hypothesis is true, that assumption is wrong. The assumptions made to create the expectation are wrong. Okay, and then so we would have reason to doubt that the null hypothesis is true. We have reason or to believe the null hypothesis is false. Okay, so we say we're going to assume the null hypothesis is true. If it's true, what do we expect to see? This is our picture of the expectation. We compare that to the reality. If they're very different, that gives us reason to believe that the assumptions that we use to make this expectation, those assumptions were wrong. Okay. On the other hand, if the expectation and the reality are very close together, if they're similar, then we have no reason to doubt that the idea that we had to come up with our expectation was wrong. Does that reasoning and line of thinking make sense? Okay. All right, so how do we measure the difference between expectation and reality? Okay, so we will measure difference between reality and the expectation. We'll say difference between reality and the expected with sample statistics. Okay, so what we'll do is we'll do observed minus expected. And so in our case, the observed will be kind of our sample statistic. Minus, and we will have what we call the null value. That's what we expect. Null value being the value in the null hypothesis. Okay, maybe I should write that. Expected would be value from null hypothesis. This is what we expect to see. The value in the null hypothesis is what we expect to see. What we actually observe, that's going to be our sample statistic. Okay, so let's just try an example here. We've got our bucket of M&Ms, and the claim is the proportion that is red is 19%. Okay, 19% of candies in the bucket are red. That's the claim. Okay, So if this is the case, what we're going to do is, we take a sample. Let's say we take a sample of 100 pieces of candy. 100 pieces, random pieces of candy. So we get a random sample. Okay, if the null hypothesis were true, okay, if the proportion of candies in the bucket that are red, if that's 19%, what do we expect to see in our sample? What's our expectation? Okay, if we're saying the bucket is 19% red, when I take a scoop of 100 pieces of candy, I would expect about 19% of my scoop to also be red, right? So the expected value is my sample should be 19% red. This is what we expect, okay? But we might get something different from 19% red, okay? And the question is, when do we say the difference is big enough for me to say it's different? So let's say I take my scoop and I get 20% red. Is 20% red very different from 19% red? No, that doesn't feel that weird, right? Because it's a random sample, we might get more than 19% red, and we might get less than 19% red. Okay, I get 20% red. That doesn't seem that weird. Okay. What if I take a scoop and I get 23% red? Does that feel like it's wrong? Does that feel like it's vastly different from what we expected? 23% red? Maybe not. Okay. Okay. Let's say someone says the bucket's 19% red. I take a scoop of 100 pieces of candy, and let's say I get 27% red. Would you say what we observed and what we expected is vastly different or is different? Would you say, okay, what about 31% red? Okay, at what point do we say this is very different, right? If I took a scoop and I got 31% red, and someone says the bucket should be 19% red, do you feel like 31% red is pretty different from what we expected to see? Okay, so this is kind of this is what we're asking. Expectation versus reality, okay? If they're very close, we're not going to say that's too different, right? If we get 20% red in our scoop and someone says the bucket's 19% red, that doesn't seem all that weird, okay? But, at 31% red, it feels, well, that seems a little funny, okay? So this is kind of what I'm asking here, okay? So we'll say scenario 1, let's say our sample of 100 pieces has 20 red. So p hat is 0.20, okay? And we ask is 20%. So here we would say the observation, the observed, basically our reality, is not very different from the expected. It is not much different from expected. Okay. All right, but then, I'll say scenario 2. Let's say we have n is equal to 100 and p hat is 0.24% versus scenario 3, n is equal to 100 and p hat is equal to 31%, okay? And the question is, when do we say that the observed is very different from the expected? Okay, when do we say that the reality was different enough from what I expected for me to doubt the initial assumptions about what to expect? Okay, that's what we want to know. Okay, well, it's not just an arbitrary, it's not going to be like, oh, at 10% it means it's different and or something like that, okay? It comes down to, well, what we're going to do is we compare what we observed. In this case, if we have 31%, 31 versus 19%, that's a 12 percentage point difference. Is 12 percentage points a lot or a little? Well, it depends on our standard error, okay? And this is where our understanding of sampling distributions come in. And we say, so earlier, and you had this in your midterm, we talked about sampling distributions. When we take random samples, how often will we get a certain value? Okay, and so now the question is, how often will we get 31%? So let me just kind of write down a few things to set this up. So kind of the question that we have is, at what point do we say that the reality, okay, what we observed, our observed values, are different enough from my expectation? At what point do we say that the reality, our observed values, is different enough from my expectation that I conclude my initial assumptions are wrong? Okay, because again, the idea here is our initial assumption is that the null hypothesis is true, and if the reality of our data is very different from the picture created by my assumptions, then I have reason to believe that my assumptions were wrong. And so the question is, at what point do I say that the reality or the data is different enough from my expectation? All right, so let's say, our expectation, or what we expected was 19% of the sample to be red. Okay, and what we observed was that 31% of the sample is red. Okay, and then our sample, where n is equal to 100. Okay, is it possible to get 31% just from random sampling? If the bucket truly is 19%, is it possible to get 31% red from random sampling? Yeah, it's technically possible. So if the bucket is truly 19% red, it is technically possible to get 31% red in a sample just from the random sampling process. All right, and so the question is, do you think that's what happened? Do you think we got 31% from the random sampling process? Or do you think that the bucket is not actually 19% red? Okay, so do we think we got 31% red just from random sampling. Or do we think the bucket has a proportion of red that is not other than 19%? Okay, so to answer this, we're going to do some math. We're going to calculate a probability. We're going to say, let's assume that the bucket truly is 19% red. Then, what is the probability of getting 31% red just from random sampling? Okay, can we do that? So, we're going to calculate a probability. Okay. We're going to say, let's assume the bucket really is 19% red. So this is our assumption. We're making an assumption here. Really is 19% red. And so the question is, what is the probability that a random sample of 100 pieces ends up being 31% red, and we'll say 31% or more red. Okay, because if we say 31% red is different enough from 19%, then that means 32% red and 33%, and everything higher will be also different enough from 19%. Okay, so this will be your clicker question. Let's assume that the bucket really is 19% red. What's the probability that a random sample of 100 pieces ends up being 31% or more red? And here are your answer choices for the clicker. I've got so we'll go ahead and let that run, and you guys can talk to your neighbors, and I'll pause the video for a moment. Okay, let's see. Okay, and that is indeed correct. All right, so I'll just go through this quickly because it seems like most of you guys got it right. So the idea here is, we have, according to the central limit theorem, p hat follows a normal distribution centered at 19%, and the question is, how often do we get 31% or more? And so we need to figure out our standard error. Our standard error is going to be the square root of p times 1 minus p over n. And in this case, 0.19 times 1 minus 0.19 over 100 pieces. And when I did the math here, I got 0.0392, just a shade under 4%. So my z-score will end up being 0.31 minus 0.19, a 12-point difference. And compared to the standard error, it's a little over 3 standard deviations or 3 standard errors away from the mean. And when we look that up, we look up the z, and we take the area to the right, which is what we want. The area to the right is 0.0011. Okay. Is that good? All right. Yes, question. I'm sorry? You cannot always assume that the sampling distribution is a normal distribution. Technically, we should have checked the conditions to see the conditions for the central limit theorem. So, the problem I gave you, I try to give you problems that meet the conditions where, we're taking a random sample. Our sample is large enough. We've got at least 10 successes and 10 failures, and it's not more than 1/10 of the population. So we'll assume that the conditions are met, or we can run through the conditions and the conditions are met, and therefore we can assume it follows a normal distribution. But yeah, technically we should check the conditions to make sure. Okay, so according to the math that we've done, this is the probability, okay? This is 0.0011. So what is this probability? 0.011. This is the probability of observing our data, because that's what we observed, right? Observing our data, or something more unusual. Okay, if we assume that the null hypothesis is true. Okay, and this is kind of our definition of the p-value, which I will formally define on Wednesday. And so what this says is that, yes, technically, if the bucket is truly 19% red, so technically, if the bucket is 19% red, then yes, it is possible it is possible for a random sample of 100 pieces to end up being 31% red or more. So if the bucket is 19% red, it is technically possible for a random sample of 100 pieces to end up being 31% red or more. Okay, but how often does that happen? This happens only with a probability I'm missing a 0, 0.0011. Okay, not 0.011, but 0.0011. Okay, so this happens quite rarely. Okay, only about 1 in 1,000. Okay, so the probability is equal to 0.0011. So it happens about 1 in 1,000 cases. So we have to choose. Well, so the question is, okay, I got 31% red. Okay, when I took a scoop of 100 pieces of candy, I got 31% red. Do you think it was because I got that lucky 1 in 1,000 sample? Or do you think my assumption is wrong and that the bucket is probably the bucket is something other than 19% red? Okay. And because it's so rare for us to get this thing, it happens only 1 in 1,000, we're going to say, I don't think my sample was that lucky 1 in 1,000. And instead, the more likely scenario here is that the bucket is not 19% red, and that's why I got 31% red. The bucket's probably something higher than 19% red, and that would be the explanation behind why I got 31% red. But yes, technically it is possible for the bucket to be 19% red, and the explanation behind my 31% red sample is that I got a crazy lucky 1 in 1,000 sample. Technically that's possible, but that seems less believable to us. Okay. So what I'm going to write here is, you know, while it is possible that I happen to get you know, we'll call it the miracle 1 in 1,000 sample. You know, we are inclined to believe, while it is possible, you know, we are inclined to believe that my assumptions about the bucket are wrong. I'll say my assumptions about, I should say, about the population are wrong, okay? So we conclude, instead, we conclude that the population, or that the bucket, is not 19% red, but something else. Okay. So again, when we do hypothesis testing, we say, if the null hypothesis were true, what do I expect to see? I expect to see 19% red. What is the reality? What did I observe? I observed 31% red. Is 31% and 19% red very different from each other? We did the math and it turns out, yeah, they're pretty different, because for me to get 31% red, that only happens about 1 in 1,000 cases. Because they're quite different, we come to the conclusion that my observation is different from what I expected. And because I did actually observe this data, then I'm going to conclude that my assumptions that went into my expectation, those assumptions were wrong. All right, I hope that, you know, I hope this logical thinking, this line of thinking makes sense, because this is what we are going to do for hypothesis testing. So this was kind of just a little exercise here, and we will formally define all of the steps in hypothesis testing on Wednesday. But I wanted to expose you guys to the line of thinking first, and then we'll talk about all of that on Wednesday. Okay, so we'll end here for today. Have a good rest of your day.